Assalamu alaikum dear students. Here we have another topic of A2 Physics 9702, and of course this is chapter number 13, gravitational fields. This is the continuation of the discussion, and here we have the lecture number 3. Today we are going to discuss the satellites, and when you will define the satellite, simply you can say that a body moving in an orbit around the earth is a satellite of the earth. So a body moving in an orbit around the earth is called the satellite of the earth. So simply first thing comes in mind that we have moon which is orbiting around the sun, around the earth. So simply you can say that the moon is a natural satellite of the earth. Similarly, if the earth is orbiting around the sun, so we can say that earth is the satellite or natural satellite of the sun. Then we have man-made bodies, and when we have this type of situation that a man-made body plays in an orbit around the earth, this body is termed as the artificial satellite. Like suppose international, we have international space station, which is just an example of your artificial satellite. Number of communication satellites we have around the earth, and all these are basically the artificial satellites. Now what about the orbital velocity, and with which velocity we will throw a body, you can say, so that body can start rotating around the earth. So this is sort of definition here for your orbital velocity. The velocity which is imparted to an artificial satellite a few kilometers, few hundred kilometers above the surface, the earth's surface, so it may start orbiting around the earth. Yani if you have a body which is not very far away from the center of the earth, only few kilometers above the earth, then we need a particular velocity with which the body will start moving around the earth. So this velocity is termed as the orbital velocity. How we can calculate this orbital velocity? So simple thing is that, as we have just mentioned, that the satellite will not be very far away from the center of the earth, and you can say when we have this situation, that height of the satellite is very small as compared to RE. So simple thing is that we can consider the distance from the center to the satellite, which normally of course you can write as R, but this R will be nearly equal to the RE in this case, because as I said that H is very small as compared to RE. Now the thing is that when we are considering the motion of the satellite around the earth, then simply we can say that here we have suppose the satellite, and of course the satellite is moving around the earth. So of course there will be a centripetal force, and this centripetal force is coming from the gravitational force. So simple thing is that we can write Fc, any centripetal force, is equal to the gravitational force if a body is, any satellite is moving or orbiting around the earth. So simple thing is that you know that your Fc is nothing but centripetal force, which is given as mv square over r, and this is your gravitational force, which is gmm over re square. So when you will simplify this equation, you will get the velocity like this, that this is equal to square root of gm divided by re. We can even use all these values, because all these values are constants, but we can further simplify this equation 1 in this way, that g is equal to capital G m e r e square, which we have discussed in the last discussion lecture. So simply you can say that gm is nothing but GRE square. So when you are using this gm and you are replacing this gm by GRE square, simply you are getting V is equal to small GRE with square root. So now you know the value of G, which is 9.81, and here you have the radius of the earth. So the approximate value of your velocity, which is orbital velocity, is 8 kilometers per second. So simply we can say that the equation 2 gives the magnitude of the velocity we have to provide to the satellite so it may start orbiting around the earth. Here I just want to mention, and you can see that when you are throwing a ball, or you can say a sort of ball or a shell from the cannon gun, then you may have this situation that slowly and gradually you are increasing the velocity of the shell, and you can see that still it is not orbiting around the earth. Even at 7 it is not orbiting around the earth, but when you will provide this velocity, which is 7.9, so it will start orbiting the earth. So this 7.9 is your velocity, which is the required velocity which we have to impart to a satellite if we want to move this satellite around the earth. Here is a very simple thing, is that a little bit about the escape velocity. So if you are increasing the velocity to 10, then you can say that it is moving in a big circle, but it is not the you can say the sort of circular orbit. But when you will increase the velocity to here you have sub 11.2, so when you will impart this velocity 11.2, you will see that your object is not even orbiting around the earth, and it will escape from the surface of the earth. So you can use the term escape velocity, but the main point here is that if we are importing 7.9, then 7.9 kilometer per second is the velocity which we will provide to a satellite, and this satellite will start moving around the earth in a circular orbit. So this is something which is very important to understand, that what is the meaning of escape velocity. The body is escaping from the gravitational field of the earth, and here you have this velocity, which is 7.9. so this velocity is the orbital velocity. So you should make this difference clear. So we are coming back to the point here, and we are now considering another thing, which is the geostationary satellite. What is the geostationary satellite? So simply you can define the geostationary satellite in this way, that the satellite that moves around the earth at the same rate as the rate of rotation of the earth about its own axis, and thus remain in a fixed position at a specified height above the equator. Yani, if from the on the equator you are observing a body which is stationary with respect to you, then you can say that this is nothing but the geostationary satellite. And why it is stationary? Because the time of rotation of this satellite is same as the rotation of the earth, which is 24 hours. So as your velocity and your time of rotation and the time of rotation of the satellite is same, so you feel that this satellite is fixed at one position. So this is one very important thing. The orbit around the earth in the same direction as the rotation of the earth, that is from west to east. Yani if you are going in this direction and there is a body which is coming with the same velocity in the opposite direction, then of course you will feel that these two bodies are moving with respect to each other. But if you have a situation like two bodies are moving parallel, and not only parallel but with the same velocity, so you can say that the velocity of suppose v1 is equal to the velocity of v2, and here we are talking in terms of the you can say vectors. So vectors are equal in the same direction. So you will feel, and both of these people will feel that they are at rest according to or with respect to each other. But these two people which are somewhere here, in this case, even the value of the velocity, any magnitude of velocity v1 and v2 will be same. Of course they will not feel that they are at rest, but they will feel that they have a relative velocity. So this is very, very important. So on the equator, if you have a body and the time of rotation is same as the velocity, the time of rotation of the earth, and it is moving in the same direction as well, yani rotation of the satellite is from west to east as the rotation of the earth. So you will feel that the satellite is at rest. So this is very, very important. And these two things, if a body is following, then you can say that we are dealing with a geostationary satellite. Now here we have another very important relation, which is the relation between period of revolution of planets and their mean distance from the sun. Like if you have a situation that like suppose here you have the situation there, here you have one body and here you have another body, like suppose this is the situation of the sun here, and here you have the earth. Then what will happen, you have to consider the distance between them from the center of the sun to the center of the earth. The distance is r. This is not only re, but who is providing the centripetal force to the earth? Of course the gravitational force which is coming from the sun. So simply, as we have discussed in the previous part, your centripetal force is not but the gravitational force. So simply we can again come to the point that here we have the situation of GREGM, and up to this we have already discussed in the previous part. So you can write GM over here, GM in terms of your small g and RE. So this is what you have. Now GM is a GRE square. So be careful. Yani here R is different and RE is different. RE is the radius of the earth and R is the simply the radius of the or distance between the body. We can consider here the situation of the sun and earth, or even we can consider here the situation of the earth and another body, like here we have a satellite suppose. So anything which we are considering, or any system which we are considering, but if you are considering RE, then of course the satellite suppose you are considering here, and of course for the sun the satellite is earth, and so on. Now the thing is that if you are considering the velocity of the body which is moving around the sun suppose, which is V is equal to R omega. So V is equal to R omega, we can write in this way, and your V square will be R square omega square. So here what you can write the value or the equation here, R square omega square. So what you have here, omega square is equal to RE square R cube. Now for omega, you know that it is nothing but 2 pi divided by T. Yani now you are coming towards the time period, or you are talking in terms of the time period. So for omega, now you can write 4 pi square T square. And when you will simplify this equation, you will get this equation which I am mentioning here as equation 1. R is equal to cube root of GRE square T square 4 pi square. So this is the equation which we have here, and this equation is giving you the relation in this way, that if you want to write the equation here, this is the equation here which is R. So you can calculate this R as well. This is basically the radius or the distance between the sun and the body, which is earth in this case. But you, as I said, that you may have any body here, and this is basically the radius between the main body or the source body and the body which is orbiting around that body. And here you have the time period, which is t square. So if you will write this equation again, you can write it in this way, that t square, if you want to make the time as the subject, so you have t square is equal to 4 pi square g re square, and here you have rq. So simply you can say that all these things are constant. Of course, if you will consider the sun, then this will be the radius of the sun. If you will consider the earth, then this will be the radius of the earth. So either way, if you are considering here the situation of the sun and the earth, then of course the r e, instead of re you will write rs. But if you are considering here the earth, so we will write re. And of course here the ultimate equation we have, which is t square is equal to r cube. And this is actually the relation which is the Kepler's third law of planets, and this states in this way that the squares of the periods of the revolution of the planets are directly proportional to the cubes of their mean distances from the sun, or from the source body, you can say. The period of revolution is independent of the mass that is orbiting around the sun. So this is also very important. And if you are considering the case of the sun and earth, then you can say and see that in the last equation we do not have any you can say dependence on the re, because re is a constant. And here, as I said, that if you will consider this fact, then simply you have to consider the distance between the center of the sun and the earth, or distance between the center of the earth and any other object. So this is very important, and a sort of relation which is termed as the Kepler's third law. So I have given you both examples, sun and the earth, or earth and any body which is orbiting around the earth. So this is what we have as far as the relation is concerned. So be careful that this is your relation, which is the Kepler's third law, and here we have the statement, you can say, of this law. Now here we have another simple situation as far as the parking radius of the geostationary satellite is concerned. So as we have just discussed, that this equation we can use if we are talking about the situation of the earth and a satellite, suppose. So if you have this situation, that here you have the earth and here you have the satellite, then of course this distance is not very far away. So simply you can say that the distance you have to consider somewhere here you have this situation. So if you are considering this equation, then what you will write here, you have this re, and of course you know that re is 6.4 into 10 to the power 6 meter. This value actually given in your paper as well. 9.81 is meter per second square is the value of g. And then you have the time period, and you know that the for geostationary satellite the time period is 24 hours. So if you want to change this into seconds, you will get this value, which is 86,400 seconds. And by using all these values, you will get this distance, and this distance is 4.24 into 10 to the power 4 kilometer. Yani, if you will consider this distance, then this distance is r, and this distance is given as 4.24 into 10 to the power 4 kilometer. Now the thing is that if you want to know that what is the height of the satellite, then simply you can simply say that the h is equal to this r minus re. So you found that this value is coming as 3.6 into 10 to the power 4 kilometer. So it means that if you want to keep a particular satellite in orbit, the orbital velocity is nearly 7.9 or 8 kilometers per second. If you will impart this velocity, the body will start moving in the orbit around the earth, suppose. And here, if you will keep this distance, then this will be the situation for the geostationary satellite. Yani, the above calculation shows that the parking orbit will have the radius of this value 3.6 Newton raised to power 4 from the surface of the earth. So we have this situation as far as the geostationary satellite and the related topics are concerned. Here I just want to emphasize this point again, then that this equation they can ask you in exam, they can ask you this relation, or even they can ask you this relation in your exam. So all these are very much related to each other, and very simply you can find these relations or equations. And this is the topic of satellites. So inshallah, see you again. If you are new on my channel, subscribe this channel and like and share this channel. Press the bell icon, so the new lectures which we will upload, you can get it immediately, and in this way you can complete your course very easily. Till the next lecture, Allah Hafiz, take care.